Welcome to our discussion on the Gauss-Jordan elimination technique for solving systems of equations. Our two main objectives are going to be able to use these matrices to solve systems of linear equations that have unique solutions, and also use these matrices to solve systems of linear equations with non-unique solutions. Okay, so let's first look at the ones with unique solutions, the ones that kind of matter the most. You may have dealt with systems of linear equations before where you write a bunch of stuff, in terms of x, y, and z, and you have to either do the elimination method or the substitution method to work your way down until you solve for x, and then you plug that back in to solve for y, and then you plug those back in to solve for z, and so on and so forth. It's a fairly straightforward technique for solving systems of linear equations. It can be a little time-consuming, and it can also open you up to making a lot of errors because there are a lot of simple mathematical processes. You're multiplying by a constant, then you're adding and subtracting stuff, and it's really easy to do the simple things wrong when our brain is kind of concentrating on something that seems a little bit more complex, like solving these multiple equations, right? So if we want to solve a system of linear equations with matrices, the first thing we have to do is have a coefficient matrix, right? So we basically create a matrix of all the coefficients of the equations. And then we also have to have the constants in there because they're always equal to something. And when we put that all together, we get what's called an augmented matrix. And it looks something like this. So here were our three equations that we had that we were going to try and solve the old-fashioned way. We can rewrite it into an augmented matrix where the numbers here, you'll notice, just represent the coefficients, right? 1, 2, 3, 1, 0, because there was nothing here. Negative 1, yet the minus signs matter. Down here, you're going to have 1, minus 1, minus 1. And then, of course, the answers, signs also matter, right? 6, 0, and negative 4. So now that we have this augmented matrix, the piece on the left is the coefficient matrix, and then these are the solutions, so we call it an augmented matrix. Well, we can now use matrix operations to solve these systems of linear equations by performing the same operations on the rows of the matrix that you would do to the system of equations, when you were doing it algebraically with all the x, y's, and z's, to be able to eliminate various variables so that you could get it down to where it just told you x equaled something or y equals something, and so on and so forth. You probably didn't recognize what you were doing mathematically when you were reducing those systems, but you were basically held to only three things you could have done. You could interchange two rows, i.e. you could trade places, you could move them around. You could add a multiple of one row to another. So you could basically multiply any row by a non-zero constant, which really we should have listed that as number 2 because we need to do that in order to do number 2, right? So if you switch places with 2 and 3, you can multiply a row by any non-zero constant, because if you multiply by 0, you just zero out the whole row, and now you can't solve it. And then the other thing, like we said, you could take that multiple of that row and you can add it to another row. You can also subtract it from another row, but it's usually safer to always add. So that just means that when you're thinking about, okay, I want to eliminate this thing and I need to be able to subtract this from this, then I'm going to multiply that row by a negative number so it becomes negative. So when I add it, I'm actually subtracting. So just keep that in mind, that you really want to hold to these three basic rules because it's going to minimize your chances of making a mistake. Now, once you put it into technology, it doesn't matter at all because technology just does it for you. So for instance, what is going to happen is when you start augmenting these things, when you start multiplying and adding and blah, 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 you're going to reduce it down. You're going to get a bunch of zeros and then just ones on the diagonal. And once you do that, you've solved the system, because this basically tells you have 1x and nothing else equals negative 0.5. You have 1y and nothing else equals 4. You've got 1z equals negative 0.5. So you basically now know that x equals this, y equals this, z equals that. It's a beautifully simple process for solving systems of equations. The elimination method, or Gauss-Jordan elimination method, is this systematic procedure that uses these row operations to reduce the matrix, right? So that's just the name of what we're doing. So let's look at another example. Here's our starting matrix. Here's our augmented matrix. Sorry, not starting matrix. Our starting system of equations, our augmented matrix. And now we can start doing things to it, right? We need to get, the first thing we want to try and do is we want to get a 1 in row 1, column 1. We want to turn this into a 1. And then we want to get, ones on the diagonals and 0 everywhere else. So in order to get that 1 up here, you'll remember that the original matrix was this one. In fact, let's bring that original matrix back in so we can see that, oh yeah, this second row used to be up here. So if we switch row 2 with row 1, we get that leading 1. We get that 1 in the pole position, right? The 1, 1 position. And now our goal is to get zeros below it. We want to zero out these two numbers. So it's really easy. All we have to do is, well, technically we could subtract the first row from the second row to get a 0, or we could multiply one of these rows, either the top or the bottom, times -1 and then add them together, and that will get rid of it, right? So the rule is to get rid of these two numbers, you have to always use multiples of the row you're keeping to get rid of the ones you want to get rid of. So you would take the top row, you would multiply it by a -2, and when you do the -2, you get -2, -8, -6, -2. Now you take that, you add it to the second row, right? The 2 and the -2 gives you a 0. The -8 and the 5 gives you the -3. -6 and 4 gives you -2. -2 and 4 gives you 2. And that's how we get the middle one. Then to get rid of this one, you're going to take the top row, multiply it by -1 and add. So that gives you -1, -4, -3, -1. Now add that to this one. The -1's cancel. -4, -3 gives you -7. -3, -2 gives you -5. And -1 plus 5 gives you 4. That's how you get that one. And now we've gotten rid of the zeros. The next thing is you want to get a 1 in this spot here. And that normally just means dividing by its coefficient. Now, here's something you want to think about. If I divide everything through by a -3, I'm going to get fractions. And fractions suck. We hate dealing with fractions. So you always want to check this row and see if this row would work better. So if I could divide everything by 7, and let's just say I didn't get fractions, then it would be better to turn this into the 1 and then just switch places with these two, right? So just keep that in mind that you can always swap those rows, especially if it keeps the math easier. But in this case, there's, nothing's going to work as far as no fractions, so we're just going to go ahead and stick with this one because I think we'd rather have thirds than sevenths. And then we just repeat the process. Now that we have the 1 there, we want to make zeros above and below, so we multiply this bottom row by the appropriate amount to get rid of it, right? So again, let's remind ourselves what this one looked like. We started with that one, right? And so to get rid of this 4, you multiply the bottom by -4 and add. And then, of course, you're going to have to do all the fractional stuff, and you get these numbers. And then to get rid of the 7, you got to multiply the bottom by 7 and add. And again, you get all these fractions. Okay, then this second column is now done. Now the third column, we repeat the process where we want a 1 down here. So we multiply everything down here by a -3, right, to turn into a 1, which is nice. We've now gotten rid of the fractions. And now using this row, we need to turn these both into zeros. So you take the bottom, multiply it by a -3, add it up here. Lo and behold, it gets rid of the fractions, brings back in a 3, which is nice. Multiply the bottom by a -2/3, add it up here, and again, it gets rid of the fractions, and we're left with this. And this now tells us that x equals 3, y equals -2, c equals 2. Ta-da! And that's That's our final solution. And you could always check it. You can plug it back in and see that it works. And because the augmented system is equivalent to the original system, we know that the answer we get for that is the same that we would get for the original one. All right, how about another example? So we've got a manufacturing company. They want to know the best use, how to best use the time available within their 3 manufacturing departments. Each one must be stamped, painted, and packaged. So here's our data. Basically, this is how much time, right, the hours required for processing each type of shed. Then, of course, we need to know how much things cost, and we need to know some constraints. The stamping department only has 32 hours to use because they only have so many workers that can work 8 hours a day. Same thing with the painting department and the packaging department. So that means that if we look at those stamping hours, right? Remember the stamping hours 2, 3, and 4. So there's the 2, 3, and 4, right? And then painting 1, 2, and 1, and then 1, 1, and 2. That's where all these are coming from. We set them equal to their maximum amount of hours, which gives us an augmented matrix. And then all we need to do is take this augmented matrix and turn it into an identity matrix by swapping rows, adding and subtracting multiples of rows, right? So in this case, we took -1 times row 1, added it to row 2 to get the new row 2. That's how the 0 went away. And then the -2 times row 1, blah, blah, blah. I mean, it would help if we saw the previous, right? If we had this, so we knew what that thing looked like to help us visualize what happens when we're doing these things. Let me make it smaller so it'll fit. And now, right, if we take negative of this row, add to this row, the zeros go away. -1 added to 2 gives you 1. -2 added to 1 gives you the -1. And then -1300 added to 1700. That's why you only have 400. Okay? Follow the same steps to get this one. Now using this matrix, we want a 1 in the middle, which we already have. So we can do -1 times it and add it to the top, and -1 times it and add to the bottom to make those zeros. Now we want the bottom one to be 1, which we already have. So we can just add it to this one, right, to get rid of it, and then multiply it by -3 and add to this one to get rid of that one. And we finally get down here. So we can see that the solution to the system is 300 hours in X1, 600 hours in X2, and 200 hours in X3. So that just tells us they should make 300 type 1 sheds, 600 type 2 sheds, and 200 type 3 sheds. And that's how they can basically use up all of their labor, right? They're not wasting any labor. Systems with non-unique solutions. So it's also possible for a system of linear equations to have an infinite number of solutions or no solution at all. And although the coefficient matrices for systems with an infinite number of solutions or no solution will not reduce to identity matrix, the row operations can be used to kind of obtain a reduced form of the solutions if they exist, and then they can be determined. So because it's not unique, you're not going to get that perfect identity matrix, but you're going to get something close to it, which is going to give you an idea of what you can do. A matrix is said to be in reduced form when it has the following characteristics. The first non-zero element in each row is 1. So basically, if you go across any row, the first number that isn't a 0 that you come across has to be a 1. And then things behind it could be other things, right? So, for instance, if you had a let's just say it's a 3 by 3, and this was 1, 2, 4. Well, that's still reduced, right? And then 0, 1, 3, that's reduced, and then 0, 0, 1. So this is technically reduced. You could then take it forward and turn it into the identity matrix if you had to, with some more operations, right? If this was a 2 or anything other than a 1, even if this was a 1 or a 0, still not reduce. Okay? Each column containing a first non-zero element for some row has zeros everywhere else. So you can see that now it doesn't satisfy that thing anywhere here, right? So if this is a 1, this has to be a 0. And if this is a 1, these both have to be zeros. So you can see that when you put this and this together, you force an identity matrix if you have a 3 by 4. Or sorry, a 3 by 3. The first non-zero element of each row is to the right of the first non-zero element of every row above it. So that gives us that diagonal thing. And then all rows containing zeros are grouped together below the rows containing non-zero entries. So basically what happens is the difference between an identity matrix and just something that's reduced is you could have a row of zeros. So if you had 1, 0, 0, 0, 1, 0, and then 0, 0, 0, it's reduced, it's just not an identity matrix. You can see that it satisfies the rules. First non-zero is a 1, everything else is 0. First is a 0, everything else in its column is a 0, and then there's nothing else, everything in the column is 0, right? So we're all good. Let's look at some examples, right? Reduced. And the reason why this is reduced even though there's numbers here is because we're only concerned with this portion being reduced. The augmented stuff, remember, are the solutions. So this one's also reduced. This one right here is not reduced. Actually, I take that back. This one is reduced because it's just, this has to be a 1 and there has to be zeros everywhere else. There is no leading 1 in this, so it doesn't matter what's going on. The next leading 1, is further back from this leading 1. It has zeros above and below, and then any rows with all zeros are at the bottom, so it does match. The following are not reduced because of this, right? There has to be zeros above every, leading 1. This one, the leading thing, is not a 1. And then this one, they're out of order. So you just have to switch these two columns, or think about it, switching the two rows. And then it would be reduced. Okay, why does this matter? Well, it enables us to get kind of like partial solutions to systems of linear equations. If you know anything about solving systems of linear equations, you know that the only way to get a unique solution, in order to be allowed to get a unique solution, right? It still might not exist, but in order for you to have any chance at all to get a unique solution, the number of rows must be equal to or greater than the number of columns. Basically, you have to have the same number of equations that you have unknowns, right? So we have 4 unknowns, x1 through x4. We need at least 4 equations or more. Well, we do. We've got 4 unknowns, right? And we've got 4 equations. So this has a chance of having a solution. If for any reason you ever have more columns than rows, you'll know right off the bat that you're not going to get a unique solution. But like I said, you're not guaranteed one. And as you can see from this example, we get down to this, and then we go a little bit further, and we get to here, and then we'd have to go, and that's it, right? Because we don't have to make this one 0, because this is the leading 1, and we just need zeros above and below it. This is nothing. There's no leading 1 here, because this one is behind that one. If it was down here or down here, then yes, we'd have to make zeros everywhere. Here's a leading 1, zeros everywhere, and this is what we've got. So it tells us that x4 is 4, but then we only know that x2 plus x3 is negative 3, and x1 minus 2x3 is 2. So we haven't come up with unique solutions, but we've come up with something that, kind of gives us a solution. It's called a general solution, where sure, one or two of them might be completely defined. And in this case, we've got x4 is completely defined. That's the only one. But the others are still defined in terms of other pieces. So then you could take each of them and you could solve for, let's bring this over there to remind us what's going on. You could solve each of these, stop doing that please, for one of the variables. So you could solve for x1 by adding the 2x3 over here. So you can see x1 equals 2 plus 2x3. And then you define x2 to be something in terms of x3. It's negative 3 minus x3. And then x4 is just 4. And then you just say, okay, x3 can be anything. And then 1 and 2 are both determined by it, right? So that's what you want to do, is you want to get all variables defined in terms of one variable, and then just say that that one variable can be anything. And then that gives you solutions to your system. Infinite solutions, right? Because you can let x3 be anything, and once you do that, then it defines what x1 and x2 are. x4 never changes. And then you can let x3 be something different, gives you a whole other solution, and blah, 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 blah. You get infinite number of solutions. So again, the reduced form of augmented matrix for n equations and n variables. Coefficient array is an identity matrix. The coefficient array is not an identity matrix with either a row of zeros in the coefficient array with a non-zero entry in the argument or otherwise. So this is telling you what happens when this happens, right? So if your coefficient array is the identity matrix, which was our first couple examples, then we know we have a unique solution. However, it's not, and we have a row of zeros in the coefficient array with a non-zero entry in the argument. So in the case of this previous example, if we came down here and this was all zeros and this was anything other than 0, like, a 1, a 2, a negative 3, a 5, whatever it is, it basically says 0x1 plus 0x2 plus 0x3 plus 0x4 equals negative 5. And you go, well, that's impossible. Ergo, no solution. However, if it's not an identity matrix, but it's been reduced, and we have that row of zeros, and that row of zeros equals 0, then we're still good. And we get infinitely many solutions, and we have to solve for the lead variables in terms of the non-lead variables. Lead variable, non-lead variable, lead variable, non-lead variable. So that's why we solved for in terms of those and got these two things. And then we have infinitely many solutions, but at least we kind of came up with a pseudo solution. All right, finally, what happens when we have non-square systems? So we have fewer equations than variables. And I already told you that when we have fewer equations than variables, there is no solution. We cannot solve it because we just don't have enough information. It's impossible to reduce it to an identity matrix. Therefore, these things cannot have a unique solution, but they could have no solution or infinitely many solutions, just depending on how the matrix works out based on those previous rules. If the reduced augmented matrix contains a row of zeros with a non-zero number, then we know there's no solution. And then otherwise, if it's zeros all across the board, then we know it has infinitely many solutions. So that's really what it comes down to, is these two things. If that bottom row of zeros is all zeros, you've got an infinite solution thing. However, if that bottom row of zeros has a non-zero number, in the augmented piece on the right, then there's no solution at all. Let's look at a basic example of this system, right, where we've got 3 unknowns and only 2 equations. So we know right off the bat there is no unique solution. But we could start trying to augment it and get it to where we can hopefully, get some sort of solution. We don't have a row of zeros, so we know we're good. It's in reduced form, right, because we've got a leading 1 with zeros above and below, a leading 1 with zeros above and below, and that's really all that matters. The rest can be anything. So that tells us that we're left with these things, right? The leading coefficient of 1, plus we had that 0, and then we had the z, right, so on and so forth. So this is basically what it looks like when we bring the variables back in. And then to solve for these, we solve for the leading ones by moving this stuff across So now everything's solved in terms of z. We let z be any number, and this becomes our infinite solutions, right? We basically define them as straight lines. And so the amounts invested are 14% at this, 8% at this, 10% at this, where we have these constrictions. You plug them in, and we notice that between 50 and 350, and y will be between 0 and 450. Right? Because if you plug in 0 for z, you get 50. If you plug in 1500 for z, right? And so on and so forth. So that's it, guys. That's how we do them by hand. We can also do this kind of stuff in technology. Okay, so let's see if we can do this with technology. So we bring up our matrix menu, and we're going to define our new matrix C. Oh, sorry. I need to define it, not recall it. Got to go edit down to C. And this is a 2 by 3. Oh, sorry, it's a 2 by 4 because we got to put in the augmented part. Okay. So now just type in your coefficients, right? 1, enter, 1, enter, 1, 1. So I don't know why that middle one was. This one should be 500,000. There we go. And then 0.08, 0.1, 0.14, and 49,000. Okay, so we've defined our matrix. So now if we go back to our matrix menu, go over to math, we can do all sorts of things with it. Let's try RRF. And then we need to tell it RRF of what. So we got to go back into the matrix and choose this one. Hit enter. Oh, all right. Let's try it again. I think I need to put the 0 around it. Go. Not the 0, the parentheses. Sorry. Close parentheses. I'll try. There we go. So you'll notice that this right here is the exact same answer we have down here in the lower right-hand corner. It does what's called reduced row echelon form. It reduces the matrix as far as it's going to go. And if it was something where you could get a perfect solution, you would have an identity matrix here, and then your solution's there. But much faster than doing it by hand, and we get this matrix, and then of course you still have to go back to the next step and use that matrix to figure out your algebraic expressions because it didn't have a unique solution. But it's nice to do it in technology. If you've got the tools, it saves you some time.